Welcome to this episode of our engineering class in material handling in factories. Today we will work on this step feeder, and I will take you through the process of preparing it for engineering simulations. Before I do, I just want to give you an introduction to the workings of this machine. So I start the simulation so we can see how it moves. An important feature of this design is the fact that it's leaning backwards like this. This means that gravity plays an important role in the workings of the machine. Furthermore, we see that the crankshaft here at the bottom drives the motion of the steps. That in turn elevates the bolts up to this point where they are dispatched onto the linear feeder. The linear feeder is vibrating, and that propels the motion of the bolts. We can see that some of the bolts are placed incorrectly at this point and are thus recycled back to the beginning of the process, while others are more successful and reach the outlet of the device where they are removed from the simulation. All right, now let's reset this model and start from the beginning, and I'll show you how to prepare it for engineering simulations. Now I have reset the model, and what we are looking at now is essentially just a CAD representation of a step feeder. What we are going to do next is to explain to Algoryx Momentum how the parts of this assembly are put together and interacting in this machine. By default, all of the parts in the assembly are lumped into a single rigid body. If we simulate this system, it will simply drop due to gravity, and nothing more interesting is going on really. So we have to start splitting the assembly into independent rigid bodies. For instance, this connecting rod, we know that it should move, and we can simply select it and say split to make it an independent rigid body. Dynamics color shows us that now this is a separate body. Let's hide some of these objects to give us a clear shot on this part of the structure. We say split. We can check dynamics color. So now we have a collection of independent bodies right there. That's not quite how we want it in this case. In fact, I want to merge these objects back together so we form a larger building block in this assembly. I press down Control on my keyboard while I multi-select these objects. Then I release the Control key to indicate the final destination of this new compound rigid body. Dynamics colors shows us the new structure that we have defined. And then the steps of the feeder, the moving assembly here. Let's fix that. Same procedure as before. Select all the objects. Say split. That makes them all independent, and then we use merge to fuse them back together into the building block that we would like to have in place for our simulation. Show all. Dynamics color. It's starting to look like something. Down here we have our feeding part that we will later on use as a template to spawn the material flow into the simulation. This should also be split and turned into an independent object. Great. If we simulate this, it's a little bit more interesting than before. It still drops due to gravity. And we also see that there's a lot of contact constraints here. And this is not necessarily bad. However, this assembly was never designed with the intent to be simulated and guided with contacts like this. So there's no built-in clearance and play into the assembly. So if you were to build this this machine in real life, it would just jam, right? Because there's no play in the model, and the same thing happens in the simulation. So here we have a choice. We can either adjust the 3D model and introduce clearance so that things can move freely, or we can take a shortcut and use joints to enable the motion of the parts and also power the machine. I am going to opt for the latter in this example. So let's create some hinges to connect the parts here. One joint between that side there and the pin. Another joint here. Another one, let's say to connect the rod with that pin over there. What else do we have? We want to connect the rod on this side as well. So now we have a number of joints. Let's try that. It's always a good thing. I encourage you to simulate often. So we are now reminded that we still haven't attached the frame to space. We do that by changing it from dynamic to static, thereby stripping it of all its degrees of freedom and its ability to move. So now it stays in place no matter what. We still have a bunch of contacts here, and the steps are unable to move because the contacts are holding it in place. Let's do something about that. The approach I take is to create a prismatic joint between the frame and the moving steps. Simulate again, and we see that it's moving. Next, we want to power the steps, and we do that by enabling the motor of that joint, set the target speed that we want, and then I'm going to just stick with the default parameter values there. Simulate again, and we see that it moves up and down just like we want. The bolt is sitting nicely there on the edge. And we want to now introduce the material flow into the machine. And we'll do that through an emitter. So let's walk through that process. We go to the granular tab, enable this part of the program, and then we want to create an emitter. It is asking us to attach the emitter to a rigid body that will represent the domain in which we are going to spawn our feeding parts. So let's create that rigid body and define that geometry. I'll keep it simple here and just turn it into a little box like this. Move it to a location that I want. We can try to simulate this now. We see that it just stays in place. It is obvious that this object is not yet a part of the simulation. So let's do something about that. We select it and move it to a component. This brings it into the simulation model, and it now begins to interact with its environment, just like everything else. Next, we turn it into a static object, thereby stripping it of all of its degrees of freedom, making sure that it stays in place. Go back to the granular tab, and again, try to create an emitter. We associate the emitter with that object. We press simulate and see that it produces particles right away. But that's not what we want. We want it to produce bolts. Let's see if we can figure out how to do that. We click on it and say that no, we don't want to emit particles. We want to emit rigid bodies. And we now have to indicate which body distribution we're going to use for this. We have yet to create one like that. Let's see if this button can help us. So this is the Algoryx Momentum Body Distribution tool. You can also find it in the granular tab right here. So in this window, we can create body distributions, and within each distribution we can add a model, and a model contains a template that defines the geometry and physical properties of the object that we want to spawn. Currently this list is empty. There is no template available in the simulation model. So that becomes our next task now, to create a template. And for that, we use the template tool. We click on our bolt, which then becomes added to our template library. We go back to body distributions, click the template drop-down list, and we find our bolt right there. Excellent. And now we can go back to the emitter and say that we want to spawn bodies according to this distribution. We should also consider the mass flow. It should be something like 0.1 kilos per second, I believe. We can try with that and see how that turns out. And indeed, it is generating bolts. It is also visualizing all of the contact constraints, which is a little excessive and makes it difficult to see what's going on. So let's disable that, and then I'm going to adjust the mass flow a bit more. Let's reduce it by an order of magnitude. That looks more like it. Can move up the ladder and see what happens. Okay, the bolts are piling up right there. We need to activate the linear feeder. Here we have a choice. We can turn the linear feeder into a vibratory feeder, or we can simply use a conveyor feature to drive the motion of the parts. I think in the interest of time, I will use a conveyor and then create a separate video where we go through how to create a vibratory feeder. Now the conveyor belt feature is located up here. We simply click on the side to route the conveyor and then specify the speed of the conveyor. Run the simulation. That looks nice. When they reach the end, they will just drop in a way that's not really what we want. To fix that and remove them from the simulation, I am going to create a sensor right here at the end. Simply by drawing a rectangle, extruding it, turning it into a component to make it a part of the simulation, making it static so that it stays in place. And then we go back to the granular tab and create a sensor. And sensors are relatively complex objects. They contain a lot of different features. For now, we're just interested in enabling its sync capabilities. We simulate, observe how the bolts are traveling up to the conveyor and then fed all the way to the sync, which removes them from the simulation. Nice. And now that we have this running, we can play with design and stress test this solution to our satisfaction. With that, thanks again for watching. A new video and continuation of this course will come up hopefully soon.